Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we've had a number of really interesting talks. I'm glad to see everyone looks alert and has a lot of energy for the afternoon session. Garnet Chan is going to start us off in the afternoon session with a lecture on quantum information and for quantum chemistry. Garnet.
Okay, thank you very much. It's very interesting to be in this meeting.
We got to get your mic.
Oh, yes, sorry. The one thing I had to do. Okay. All right, now we can start again. Okay, so as I was saying, it's really very interesting to be here and to meet all the different people in a different community, and also to be in a different setting. So I think I was telling Marcus this is the first time I've been outside of an academic environment. It's not really so different. It's just, the food is nicer and the chairs are nicer, but otherwise it's kind of similar. So that's me. Let's see, does this pointer work? Okay, so my name's Garnet Chan, as you heard. I'm now on the faculty at Princeton, but for most of the last decade, I was in the chemistry department at Cornell. So my talk today tries to look at some of the intersections between quantum information theory and quantum chemistry. I'm by training a quantum chemist, but in recent years there's been a lot of marrying of the two fields, and that's symbolized by these two figures here. It's the ones, I don't know which one is which, but one's supposed to be quantum chemistry and one's supposed to be quantum information. You can see they're not really so different. They differ, in fact, only by one line in PowerPoint. So I don't usually think of myself as working in quantum computing. Rather, I would say that my group works at the intersection of quantum chemistry, condensed matter theory, and quantum information theory. And what we try to do in our work is we devise numerical methods drawing on concepts from these three fields to simulate molecules and solids with high accuracy and with material specificity. Now, some of the problems that we're interested in are shown here. For example, I'm interested in the area of strong correlation. That's also the title of the next talk you'll hear about from Matthias. But briefly, this is a scenario for electrons when the energy scale of the electron interaction becomes large or dominant. And in that case, the traditional mean field picture breaks down. We're also interested in devising new simulation methods to treat very large biomolecules or even infinite systems such as condensed phases, including things like metal oxides and superconductors. And then finally, we're interested also in quantum dynamics. This is what happens whenever you carry out a spectroscopy experiment in chemistry. You shine electromagnetic radiation on a system, and it relaxes, and through its relaxation, you try to infer the properties of the system. So all these areas are classic. All these areas are classic problem areas in chemistry and physics, and they all lie at the frontiers of classical simulation. Now, they're of course very challenging to carry out, particularly for large systems. And so we really have two choices. So one, we can say the classical simulation is very difficult, and so consequently, we should try and go through the route of a quantum computer and take advantage of quantum computing to make progress. Okay, and of course, that's one of the reasons why we're meeting here today. But the other way in which you can try to improve things is to say, well, perhaps we can improve the classical algorithms themselves. Indeed, there's no indication that the optimal classical algorithms have been found. And so a fruitful way to improve the classical simulation algorithms is to incorporate insights which have been gained from quantum information and quantum complexity theory in recent years. I don't quite understand how this clicker works. So the click to the right. To the right. Okay. Okay. Okay.
Oh, there it is.
I think it's to do with where I've clicked here. Okay. All right. So that works now. Okay. All right. So so at the very heart of it, if you take away the sort of the applications to the real gory chemistry, quantum chemistry is really concerned with three foundational fundamental problems. Okay, so the first is a sort of existential problem. Why can we do quantum chemistry? If you think about the vastness of Hilbert space, that suggests that it should be impossible to ever simulate quantum mechanically a large biological system like a piece of DNA. But the fact is we do that. In practice, we can do that, at least within some approximations, reasonably well. And so why is this? Does this mean that nature is in fact much simpler than we expect? Right? If indeed nature is then simple, this leads us to the second sort of foundational question. What are the kinds of quantum states that nature explores? Okay? What structure do they have? In condensed matter, this is related to the classification of electronic phases. And then finally, on a practical level, the third question is, if I know that there are certain structures of quantum states, can we take advantage of that structure to carry out efficient calculations and construct new algorithms? So I say that these are the questions, foundational questions for quantum chemistry, but of course much of quantum information theory concerns the same questions. And so the two fields are, in fact, in my view, very closely related, even though not all practitioners always think so. Okay. Nonetheless, the different academic heritage of the two fields means that quantum chemistry and quantum information have come up with different kinds of answers to these different questions. And it's exploring sort of the intersections of these two different approaches, which I'm going to be concerned about in this talk. Okay. I'm getting confused by this setup. Okay. So quantum information and quantum chemistry view Hilbert space in a complementary way. Okay? And this leads to different ways to characterize and approximate quantum states. So in a nutshell, the two views, broadly speaking, are the following. So the formalism commonly employed in quantum information is to write your quantum state vector in occupation number representation. In this case, the basis states are labeled by local degrees of freedom. These could be local fermion occupancies, or in other words, you can map them to local qubits. The important feature of writing things in this form is that there's always a tensor product structure to the space. Okay. The traditional view in quantum chemistry, however, is a little bit different. In quantum chemistry, we typically write a state in an excitation representation. Now, what this means is you take your complex quantum state and you write it in terms of deviations from a simpler quantum state, which you know how to handle. This is typically a mean field state. From that mean field state, you then add on deviations or excitations. In this basis, the excitations involve labels which label individual electrons. And so this is more of a sort of first quantized view. Also, from a mathematical perspective, this excitation picture doesn't really have any kind of product structure. Okay. So how do we construct approximations in these two pictures? Well, I'll start off within the excitation picture, which is the one which is most familiar in chemistry. So we've seen this type of diagram already in Jared's talk. In the excitation picture, we say we start with a state which is very simple, typically a mean field state, which is made up of single particle orbitals, which are all occupied, and some unoccupied orbitals, and there's typically a gap between them. And then they add on the deviations where the occupied orbitals are moved to the unoccupied orbitals. Okay, and the way to construct an approximate quantum state, of course, you can parameterize any quantum state in this way, but the way to construct an approximate quantum state is to limit the number and form of these excitations in some way. And this gives rise to many, many different theories in quantum chemistry, probably the most successful being coupled cluster theory, which assumes there's a certain cluster structure to these terms. So this is a remarkably successful picture of a lot of nature. You can do accurate coupled cluster calculations with accuracies rivaling the best things you can measure on systems with more than 1,000 orbitals. Okay, we've been talking earlier about doing simulations on maybe 50 orbitals, but if your quantum state, true physical quantum state, happens to be reasonably close to a mean field state, then you can simulate many, many, many degrees of freedom. Nonetheless, it's clear that this picture has to fail under certain situations. In particular, if we're in a regime of nature where the typical interparticle interaction is very large compared to this gap, okay, that's called the strongly interaction regime, then this mean field picture, then the mean field becomes unstable, and this excitation picture must break down. Okay, so that's how people construct approximations from an excitation picture. What's the natural framework to construct approximations in occupation number representation? Well, this involves limiting the amount of the entanglement in the wave function. So first, let me say a little bit about entanglement. Of course, all of you know about entanglement, so I'll be very quick. Okay, so what's entanglement? Well, we know what entanglement measures to some degree is how independent subsystems are in a total system. So imagine that we have a system made of 2 qubits. If the two systems were, in fact, completely independent, then the quantum state would just factorize. Okay? And we then would say there's no entanglement. Okay. Now, in the general case, the quantum state will not factorize, but we can write it in a factored form by using a single value decomposition. In that case, the quantum state is written as a sum of the components associated with the individual qubits. And the number of terms in the sum, or depending on basically these singular values here, measures the amount of the entanglement in the state. Okay. So from this perspective, I'm using entanglement as an analysis tool. If I give you a quantum state, I can do an SVD on it and then measure how entangled it is. But you can turn this viewpoint on its head and use it as a way to construct approximations. So, for example, you can say, well, why don't I limit myself to consider only those quantum states which have a limited amount of entanglement? Formally, this means that they have the mathematical form that they can be written as a sum over product terms over qubits, and there's a limited number of terms in the sum. Okay, so that's the basic low entanglement approximation. Okay, so this can be generalized from 2 qubits to 3 qubits. So in the simplest case, if all these things are independent, then you say your state factorizes. But in the more general case, if I want to construct a low entanglement approximation, I say it won't exactly factorize, but I write my quantum state as a product of terms, each associated with 1 qubit, and have just a small number of terms in this sum. Okay, so that's my low entanglement state here. You'll notice when we write it out, it's missing a J here. You notice when we write it out, it's kind of a little bit unwieldy because they were summing over all sorts of indices and so on. So it's nice to introduce a graphical notation. In this low entanglement approximation, every qubit is associated with a mathematical tensor, some object with several indices, and I can write this tensor in this diagrammatic form where each of the legs represents one of the indices. And then in this low entanglement wave function, I've just connected those tensors together, equivalent to summing over these indices I in a certain way. Okay. So,
what do the sigmas represent?
Oh, those are singular values. So if you were to cut your system here, pardon?
Are they scalars?
Yes, this a diagonal. You can think of this as a diagonal matrix or self-scalars.
Okay.
Yeah. So if you were to cut this here, these sigma i's would be the numbers that enter into the entanglement entropy. Okay. So
they're all ones. So they're the Schmidt decomposition waves.
Yeah. So these are the Schmidt numbers if you were to decompose between the second and third qubit and the first qubit, right? And these are Schmidt numbers if you decompose them. Okay. So okay. So it turns out these low entanglement states have a name. In quantum information theory, they're called matrix product states. But in fact, they have 2 names because it turns out that this class of quantum states is a class of quantum states implicitly explored by a very famous algorithm in condensed matter, the density matrix renormalization group. So the density matrix renormalization group is probably one of the most powerful quantum simulation tools, especially when your quantum system has a certain geometry, a kind of one-dimensional geometry. What has quantum information brought to the study of the DMRG? Well, the traditional view of DMRG was in terms of sort of the statistical physics language of renormalization. And that really implied this linear connectivity of these tensors. But in quantum information theory, if we see the DMRG as being just a certain mathematical form or the certain graphical form, you can construct other connectivities of the tensors which generalize the technique to new states. And so let's look at some of these generalizations which are known as tensor networks. So here I take my qubit, and I associate again with a mathematical tensor, but instead of 2 legs, I add 3 legs now. And you can connect this now in more complicated ways, like you can connect to make a tree, or you can connect it to make a lattice, and so on and so forth. Okay? And so this gives rise to many, many different families of tensor network states. And in total, matrix product states and their generalizations have significantly advanced our ability to treat strongly interacting systems in real simulations, because you notice in their construction, I never made any reference to a mean field. Okay, I never said, well, let's start from a mean field and consider deviations from it. I just built the state up directly by linking together objects associated with each individual qubit. Okay. Why are tensor network states useful in nature? So if the success of the excitation approximations in chemistry reflects the fact that interactions are to some extent weak in many regimes, the success of tensor network states is a reflection of the fact that nature is local. Okay? So the precise, sort of more mathematical statement of locality is in terms of a property of the entanglement known as an area law, which is a little bit confusing if you call it an area, so I'm going to call it a perimeter law. Okay. So what's a perimeter law? Well, let's take an arbitrary quantum system. And let me cut it like this, okay? So I'm going to have an inner region and outer region. And you can ask the question, how much entanglement is there between the inner and the outer region? Well, we know that in physical reality is relatively local, right? So in the sense that, if I tap something over there, you don't see something pop up, on the other side of the room. And so consequently, you'd think that out of the quantum states in A and B, which are entangled, the ones which must be entangled must be the ones that live only along the perimeter. Okay? And so this can be turned into a more precise statement, which says that the entanglement entropy of the system scales only like the length of this boundary. And this is a statement which is essentially proven in 1 dimension and which is believed to hold for physical systems in 2 dimensions. Okay. So an implication of this area law, an implication of this locality, is that the corresponding quantum states can be efficiently represented by these tensor networks, which have this very, very local entanglement arrangement, right? I just have these bonds which connect these tensors on qubits, neighboring qubits. Okay. So to summarize, the 2 families of quantum states that we have for efficient simulations in Hilbert space are the following. So this is Hilbert space. And we have 2 families. We have the family of states that arise from this occupation number, quantum information picture, that are computationally efficient because nature is simple, because entanglement's local. And for these states, as I increase the amount of computational resources I devote to a problem, this allows you to capture more and more entanglement. Okay. On another side of the Hilbert space, you have the states associated with the quantum chemistry excitation picture, which essentially states nature is simple because interactions are usually weak. And here, as I increase the amount of computational resources, this allows us to extend the simulations to large and larger values of the interaction parameter. The interesting question, of course, for quantum computing is to what degree can states reached by quantum devices, the black boxes that Jared mentioned, to what extent can they live in regions outside of these areas? Okay, and that's not entirely resolved. Okay, so for the rest of this talk, I'm going to primarily just give you an overview of what applications of these simulations techniques really look like in quantum chemistry. In particular to difficult problems in quantum chemistry. So this is an area which my group has worked on for the last decade. Okay, so here's a very simple application. Let's take a fake molecule made of the simplest atoms, which I hope you remember the hydrogen. Hydrogen is the simplest atom. Okay, I'm just going to stick all the hydrogens together on a line, so it's not very simple. And when I take this linear type molecule, if I stretch it, you just stretch the line, you can show that changes the gap of the system and it moves it from a weakly to a strongly interacting regime. Okay, so it's a nice test system. Okay, so formally, the Hilbert space of this problem is very large. It has 10 to the 28 degrees of freedom. But I can ask the question: well, is the quantum state of the system well approximated by a low entanglement wave function or matrix product state? Okay, so I can construct such a low entanglement wave function by writing down a tensor associated with each qubit or each atom and linking all the tensors together. Okay, that's going to be my approximation. And what you see if I use this kind of state to variationally obtain the energy, well, here's a table of numbers. But what this index shows here is essentially the number of terms in this summation. And here are various bond lengths as I'm stretching. And you can see these are the energies. And the energies are converged to all the digits, which really means I have, at least as far as chemistry is concerned, an exact solution of the problem, okay, even though the Hilbert space size is very large. Why could we obtain an exact solution? Well, it's because there's very little long-range entanglement. In particular, if I have electrons in some bond here, they are not entangled with electrons in some bond there. Okay. So this is a model system, and I can show you many more things like this. But let me now show you some more realistic applications. And so I'm going to turn from the hydrogen atom, the simplest atom, to transition metals, which are very complicated atoms. Okay, transition metal atoms are very complicated because they have things called d orbitals. And these orbitals, if you take sort of a big atom, these orbitals are sort of shrunken to the inside of the atom, and they overlap very poorly with each other, and this gives rise to very small energy gaps in the system. And consequently, on that scale of the energy gap, the electron interaction appears to be very large. Consequently, transition metal systems have giant amounts of degeneracy in their spectrum and give rise to highly flexible electronic structure. They exhibit many, many different electronic states. It's no surprise that these transition metal systems are both the most complicated systems to study in molecules, as well as the most complicated systems to study in physics. So if you take any sort of exotic phenomenon like high-temperature superconductivity, it always involves a transition metal. OK. I'm going to focus on transition metals in biology or bioinorganic systems, and we've seen some of these systems already in various talks. Here are two very important reactions. Okay, photosynthesis, which powers the planet, right? So this, in photosynthesis, light is used to convert water into oxygen. Actually, so I've got this the other way around. But OK, so light is used to convert water. And nitrogen fixation, okay, which allows animals to basically build up protein. OK, so in both these processes, what biology does is something which appears remarkable to the chemist. So Marcus already mentioned that to carry out this reaction, what humans do today, it's actually the most important industrial process today, right? The Hubbard process. You have to carry out at 200 atmosphere pressure and 400 degrees Celsius. And this just occurs naturally in the root systems of legumes, okay, at ambient temperatures and ambient pressures. Similarly, this reaction occurs with high quantum efficiency. And so how does nature achieve this? Well, it uses a very flexible correlated electronic structure of transition metals to carry out this remarkable chemistry. And it's one of the big unsolved mysteries of our time, exactly how it's doing this. If we knew how it's doing this, then we could try and do it ourselves. OK. So I would say up till a few years ago, trying to directly understand the quantum mechanics of these systems was considered impossible. But with the advent of very efficient algorithms that use these low entanglement approximations, we can now use tensor networks or density matrix renormalization group to directly simulate the many particle quantum mechanics of these biological systems and study them at an entangled level. So I'm going to give you two examples today from my work. So I'm going to show you a study on the oxygen evolving complex in photosynthesis, and a study on something which is missing. It's somehow, I don't know what happened to this image. It looks more interesting than this, I can assure you. A study of the ion cluster of nitrogenase, what is converting atmospheric nitrogen into ammonia. Okay, so one of the reasons why it's been so hard to study these systems, quite aside from doing the quantum mechanics, it's been hard to study them experimentally even, is because people haven't really been able to crystallize out the relevant proteins, and people don't even know where the atoms are in these complexes.
That's not true.
Well, I'm going to show.
For both systems, though. No. There's an X-ray structure 2 years ago.
Yes, I know. So I'm going to show. I mean, traditionally it's been hard, right? So now we've got the structure. Okay, so I'm saying traditionally this has been so my point is one of the reasons why it's been hard traditionally to study these things is that you haven't had a good structure, and it may sound like a very simple thing to just take the X-ray structure of a protein, but it's really, really hard. If you examine the Nobel Prizes in chemistry over the last 2 decades, probably half of them go to structural biologists, where you can say all they've done is wait for a long time till something crystallized and then put it in the, in the diffractometer. But of course, it's not as trivial as that. That's only how a theorist sees it. So the amazing thing about the oxygen evolving complex is last year, an X-ray structure at atomic resolution was achieved for the first time by a Japanese group. So people finally knew where the atoms lay. And so what we decided to do was to try and study this system now, not just at the atomic resolution, but at the resolution of the electrons by carrying out a DMRG calculation. And I can't tell you everything about what we learned from this calculation, but it revealed some very interesting things. So the first thing that we noticed is that the cluster that they studied, it appears to be damaged by the X-rays. So the X-ray diffraction structure is believed to be in a certain state called the S1 state. That just means there's a certain number of electrons on the system. But if you sort of study the geometric parameters, this is in disagreement with some other spectroscopy. If we actually carry out the direct simulation, we actually can show that at this structure, this S1 state is unstable, and it's actually a different oxidation state of the cluster which is involved. The S1 state lies in a different potential energy surface. So this is not that surprising. When you stick something in a big floppy organic biological molecule in the X-ray machine, even if you're very, very careful, it's not unusual for the X-rays to knock electrons off the atoms and change the structure and change the oxidation state. But our calculations show that this is what was happening. We also did things like compute various entanglement indicators, and this says something about the reactivity. I mean, there isn't a direct link between entanglement and reactivity, but you have a sort of indirect link in the form of quantum monogamy. So you know that to some extent, if you have more partners, you can be sort of less. You can't be as entangled with each of them, right? That's the monogamy theorem. And so.
What you even mean by entanglement? Because at the beginning of your talk,
I talked about bipartite entanglement.
Right, but
yes.
You said from the quantum chemistry point of view, you started from perturbation off the mean field state.
Yes.
And
that's not what I'm doing here.
Oh, this is more from the quantum information.
Yes,
The ordinary sense of entanglement.
Yes, this is the ordinary sense. So I'm using here an approximate wave function structure. That's within the DMRG, which is in the occupation number form. So here I compute sort of the this is the quantity also which Marcus showed. I compute, I guess I don't know the precise name of this. Probably the 2-orbital mutual information is probably the right term. And this maps out basically how all the different atoms are communicating with each other in the cluster, and you can see that in the different structures, as the enzyme is going through its cycle, there's one atom which stands out as changing very significantly in its entanglement. And people have been wondering, what is the atom in this cluster which is responsible for doing the chemistry? Well, most likely it's going to be this atom. So this is of course just a pretty picture. A graph that's flattened out in some pretty way. But on each of these atoms, we have a set of atomic orbitals. And I compute the 2-orbital mutual interaction for every pair of atoms. Do you sum them up?
What do you do? I mean, the mutual information is defined between 2 orbitals and not 2 atoms.
So every atom has many orbitals. So you notice here, manganese 4, these are the 5d orbitals.
So you collect all the orbitals in I don't.
So the arrangement, so the precise arrangement of where these things are is determined by the graph plotting software, which is just trying to make the graph look understandable.
I think the question is, every circle is an orbital, isn't it?
Every circle is an orbital.
Every circle is one orbital.
And then the only meaningful information is the labels of the orbitals and the thickness of the lines. Right? The relation of the orbitals in space to each other is not important, but the thickness of the lines indicates the amount of entanglement or the amount of mutual information. So you can see that manganese 5 here goes from being essentially not entangled with anything to be extremely strongly entangled in the S1 state. So this is the atom which has a very big change in its quantum nature and is most likely responsible for the chemistry. Okay, so that's an example from.
So proximity is roughly correlated with entanglement as well.
Proximity, you said, means nothing.
No, the proximity in the graph is not very important, but that's determined simply by. Have you ever used things like graph viz? I mean, you just put graph.
Looking, how do you look at the manganese and say that it's not entangled with anything there and it is over here?
Oh, so if you look at this here, you see that none of the lines are very thick, whereas if you look at this manganese oxygen, it has a giant thick line around it, so thick it's enveloping both.
Okay, but it's not entirely clear to me just looking at the left that it doesn't have a lot of lines connected to a lot of different things.
Oh, okay, so yes, okay, but
entanglement presumably adds up.
yes, but so these are all really small numbers, and this is it's a giant number. Yeah, I mean, okay.
I'm sorry, the structure also changes, no?
Yes, the structure changes. Yeah.
Did you show us the two structures?
No, I mean it's not. I mean,
structures?
yeah. So for example, in this graph here, so this is one structure. This is the structure, the X-ray structure, and then this is a relaxed structure, which is in the S1 state, in the S1 oxidation state.
What are the two atoms that are strongly entangled?
It's a manganese 5. It's the one is on the edge here. It's on the edge of the cluster. Let's see. So this one here, this one here, or this one here, or this one here.
In the left figure, it's only 4 manganese with.
Oh, we call calcium 1, so then.
Okay.
Sorry. Yeah, sorry. Yeah. Before that's the experimental thing. I mean, it's not my fault. Okay.
So the thickness of the lines,
Yeah.
these pictures, is the singular values that appear in some tensor network.
So actually not. So this is a reduced quantity. So you can get this from the two-particle reduced density matrix. Okay. So this suggests that this is where the water is binding. Okay. Onto another system. Okay. So onto the nitrogen. Okay.
So, but you don't feel like, so the manganese 2 connection to oxygen 8.
It doesn't change.
I mean,
Yeah, I mean, this also changes a lot. But manganese 5 basically goes from being sort of not communicating with anything to being sort of deeply involved in the system. This is not a definitive. This is by no means a definitive proof. I mean, of course, what you see as a theorist is we calculate these things at these two different structures. We look at this entanglement and we go, what can we say about it? Okay, and it looks like this is this seems to be a big change.
But Garnet, you look at what happens if water is really binding.
Yes, of course we should do more calculations, right? I mean, of course we should study the whole cycle, but.
And I mean, there are these EFT calculations around by Siegbahn.
Yeah.
Is that also what he sees?
Siegbahn's calculations also implicate this atom.
Sorry, the statement was you think that's most likely where water binds because that's what you're seeing is having the biggest change.
Yes, of course. So there's a lot of context there. Okay, so why water? Why not methane or something like that? Okay, so we know that during these geometrical changes. At one stage of the geometrical change, what happens biologically is the water comes in and binds onto the cluster. Okay, and so you would think that what has happening in nature is the cluster has changed so that one of the atoms becomes available to bind water, and so we're hoping to see some echo of that in the entanglement or in the wave function of the cluster at a different structure. So this is the basis of saying that this is a possible water binding site. It seems to be doing something. It's an indirect measure. The more direct way to do this is to do the next calculation, which is to study the system with water attached and all these other things. And that's, of course, what we're going to do next.
Is there any intuition specifically as to why having an increase in entanglement with some other thing in the molecule would make it a more likely place for something to bind?
So I mean, this is why I just say there's a greatest change in entanglement. So all this is saying is that the electronic situation, the electronic surroundings of this atom is changing a lot during this cycle. Okay? Perhaps it's not being used for anything, but it's the kind of thing where, if you see smoke, then perhaps something is going on. There isn't a direct, in this calculation, there's no direct way to say that water is binding there because there is no water in the calculation.
Are the ions moving in this transition, or is this just the electronic state is different?
The ions are moving a bit. They're not actually moving very much. It's actually, they just move a tiny amount. If you were to see the two structures, you wouldn't see any difference between them, but the entanglement changes a lot.
I see. So that's like a better measure in your mind than just looking which part of the molecule has its shape changing locally the most.
Well, it's a better measure for me. I mean, the people, of course, who study the system forever, they're sensitive to minute changes in the system, and.
I mean, maybe for what? I mean, there is a direct relationship between entanglement and correlation.
Yes.
And correlation, you're forming bonds, so this is why you see the changes.
Yeah. So generally, you see this. You see these thick things happening when there's some. This indicates there's some spin pairing of the manganese with the oxygen, and this is changing the spin state of the manganese. And then this might be preparing it to be, chemically active. All right. And we were just happy we could compute the quantum state, honestly, for this thing. Okay. All right. Now, next, onto the iron-sulfur cluster, where there's a more definitive result. So,
you're not very lucky with iron-sulfur clusters.
No. I mean, this will be kind of bad. We can't see anything. Okay. So I think this is a Mac to PC conversion. I think.
And you have a magnet if you want to move your find out.
It's okay. It's okay. We can. So just imagine that there's some complex system, but embedded in it, there are 4 iron atoms. Okay, so this is a very important system, and you have all these different iron atoms which have spins. Okay, you can think of them as gigantic qubits. They have spin 5 halves, and they form many magnetic levels. And the way in which people have understood the magnetic levels in the system has been very indirect. I mean, what you do is you do an experimental measurement of something like the susceptibility, and this gives you some sort of vague featureless curve. And then you fit this susceptibility to an underlying model Hamiltonian, which you guess, to back out the magnetic levels. Okay, so this is something which now a system which we can just, again, directly simulate with the DMRG and calculate these levels directly. Okay, so these are all the singlet states that we get out, and they won't mean very much to you. But the interesting thing that we found when we calculated these singlet states is that we didn't obtain the same number of states, which is a very qualitative thing, as what previous pictures derived from experimental data had said. Okay, and actually, usually when a theory disagrees with the experiment, most of the time you're wrong. Usually in theoretical chemistry, most of the time the experiment is right. But it turned out in this case, when we looked at it, there was something wrong with the experiment. So it turns out that the Hamiltonian that they were using to back out their indirect data was incorrect. And to explain it, it's actually very simple. We have 4 ions. They each get paired into singlets, and there are 4 ions, so there are 3 ways of pairing it. And each of these 3 singlet pairings then gives rise to a ladder of excitations. And then according to the experimental picture, each of these 3 pairings gives rise to a ladder of excitations. But it turns out that when we went through and redid the derivation that people had carried out before, but more carefully, you see that those excitations are not linearly independent. Okay, so the experiment was, so they're just overcounting states. Okay. And if you look at who did the derivation, it was the experimentalist. So this just all we learn is never trust experimentalists do a theorist job. Okay, all right. So the previous calculations were using the DMRG, or the matrix product states, but more general tensor networks are also promising. For example, we showed that a generalization called correlated product states could be used to describe magnetism in these gigantic magnetic molecules, okay, with lots and lots of ions. And when you draw these tree tensor networks, then they look like they should just naturally fit into molecules like this, dendrimers. And these are very interesting for their optical properties. So I won't talk more about this. I should just move on. There are other applications of quantum information ideas. For example, quantum information has, certainly in our group, significantly influenced how we think about the idea of quantum embedding. So this is a question where if I take a very complicated system, I just cut out a small chunk. How do I capture the effect of the environment on this small subsystem? Now, there's a traditional physics way to think about this in terms of Green's functions and self-energies. But from a quantum information perspective, you say, well, all you have to do to represent the environment is understand the entanglement between the two. Okay? And this gives rise to a new embedding formalism. Also, as I mentioned, we're interested in time-dependent simulations, and we can ask how does quantum information inform them. Just to show you very quickly, the final slide, this is just to show you that the embeddings based on entanglement actually outperform traditional techniques. Again, this is a system, a chemical system, where we compare against the standard traditional physics technique, dynamical mean field theory, and the entanglement embedding does much, much better. OK, so to conclude, quantum information really has a natural intersection with quantum chemistry, and I hope I've told you about a few of those things which excite me. Entanglement theory and tensor networks have already impacted real chemistry, okay, real systems. It's not just at the level of molecules, it's really things at the frontiers of understanding. And ultimately, though I haven't really said anything about quantum computing, I think better understanding the limits of classical simulation is essential to understanding the limits of quantum simulation. So that's that.
Do you have time for a few questions for Garnet? Anyone has any?
Marcus, yeah.
Maybe you could also comment on, say, given the capabilities of, say, EMRG, what would you say a quantum computer needs to achieve in order to be competitive with the methods we know, in terms of electrons in active orbit?
I really think that for low energy properties, my personal feeling is that for low energy properties of materials and things like ground states, we have so many indications that physical ground states are really simple. I mean, except for perhaps some extremely exotic thing constructed in some weird low temperature laboratory with some peculiar topological properties, almost anything that you actually, anything you care about in chemistry isn't really that complicated, and and for that reason, I can't see the features that people usually tout as being important for quantum computing as impacting the study of these types of states. Now, in the case of the study of time evolution of quantum systems, there we know that there we don't have similar results to tell us that if we track the time evolution of a quantum state, that it's simple. In fact, we have results which show the opposite, okay, that arbitrary time-evolved quantum states are complex. And that's a regime where quantum computers are basically known to work well. Okay, so I think that for quantum dynamics, there's a lot of room. But for a lot of the problems of quantum chemistry which are not dynamical, my view is that there isn't. My view is I would bet on I would stick with improving the classical computer. That's my perspective.
Are there other questions or comments? Well, before we thank Garnet, let me ask you a question. Could you turn your last comment around and use your knowledge of ground states and how generically they're rather simple to analyze classically, or not that simple, but could you conceive of an example where the classical techniques would break down rather quickly? So in other words, can you imagine, some molecule or material where even to get at the ground state you would need quantum methods?
Yeah. Most of these. So there are definitely systems which remain hard. So probably the most difficult thing, I would say, in the classical simulation is that though representing the quantum state can be simple, nonetheless finding it can be hard. So if you're sort of cooling in a classical sense, I mean, we often overlook this point if we know we can represent the state well. But if the sort of cooling surface, so to speak, is very glassy, then it may be very hard to get there. So of course, the classical computer has problems with this. But the quantum computer may also have problems with that. But it might be that quantum computer has different problems and better ones. Probably Matthias has some some views on these types of this question as well. You can definitely make class of states which classical computers have problems with. And then I think it's still an open question if quantum computers can do that.
Yes, Peter.
So in your H50 example, obviously that's a one-dimensional train, and the Entanglement is, again, you have some simple geometric structure. Could you make a general comment about the role of geometry in the success of these methods?
Yeah, so I mean, everything that, everything people have used to build in sort of simple entanglement structures into a quantum state have induced a geometry on the problem. And it'd be very nice to relieve this constraint. Every time I see Duncan Haldane, he says, can you get rid of the lattice or something? And then, but I don't know how. Okay, so I don't know. I don't know if it's a fundamental feature or not. But currently, I don't think there's any.
I mean, there are some tensor network states that get rid of geometry entirely.
Well, yes.
I mean, we've done some of that for quantum chemistry, but
yeah. So these are
the problems.
Yeah, there are other problems. So the magnet, the giant magnet, that was also using a state which basically everything's connected to everything else. Yeah. They don't seem to work that as well as the ones which have real geometry.
Well, if there are no further questions, why don't we thank Garnet again? And the next talk is from a gentleman you've seen before. Requires no introduction.
Thank you. Okay, so I want to now go away from chemistry a bit more towards physics. We tried to invite more people from physics, but they all they had the meetings at academies or in Brussels or in Washington or somewhere. So now, unfortunately, I have to talk again. And I try to keep it in time so that we can have the nice dinner soon. What we are interested in is the material with exotic, interesting the properties that come from the strong correlations. The most famous example being the superconductors. Superconductivity was found first in 1911. Then it took nearly 46 years until it was explained first. And then the big surprise came that, okay, so the highest critical temperature was about 30 Kelvin. Then suddenly in 1986 it started jumping up. It jumped up to 140 Kelvin and it has remained there ever since. The question is, why, when it jumps so high, why can't it jump just in another factor of 2 and we're at room temperature? And with power lines that are loss-free and trains that just glide and so on, there was this big hope. But we haven't found it yet, so we might want to think about a quantum computer to give us a room temperature superconductor. Why a quantum computer? We can simulate these materials with DFT. It just gives totally qualitatively wrong states. If you look at the undoped parent material of such a lanthanum cuprate, you look at the band structure, you see a beautiful band, the D band here, crossing the fabric surface. Its half-field is a metal. If you build it, if you measure it, it's an insulator. It's just qualitatively wrong. So one has to go beyond the DFT and try to solve the full quantum problem. What people did in physics first is we like to simplify. We like effective models that capture the relevant physics. So one simplifies from the material. One sees there are planes of copper oxide. One looks at them, one goes further down and finds out the relevant is the 3D x squared minus y squared of orbitals. So we make a simplified model of just those orbitals. We throw away the rest. The only thing we keep is the hybridization between the nearest the neighbors on the square lattice. And the Coulomb from n to the 4 terms, we keep only the local u terms, so we go to n terms. And this is a simple model, the Hubbard model. And as long as we don't understand the Hubbard model, there's no reason why we should understand the full material. I will then come back later towards materials. But even solving that problem is exponentially hard. My master's thesis more than 2 decades ago was I should solve this by quantum Monte Carlo, and after that we realized, hey, there's a sign problem. So I haven't solved my master's thesis problem yet, maybe that's why I'm so interested in this. So what happens here is the Mott transition. And if we have a non-interacting system, then we have a band that is half filled, it's a metal. As we increase the local interaction, the density of states changes. As we make it bigger and bigger and bigger, the band starts splitting into 2 subbands. What goes on here is that if the on-site repulsion U is very large, the electrons don't want to move just because we don't want to have 2 electrons on the same orbital due to the strong Coulomb repulsion, and it becomes insulating in the half-filled case. The bands start splitting into 2 subbands. And this is just not captured by DFT. When you have materials close to a Mott transition, important things happen. Here, we're looking at the lanthanides, and we're looking at the volume as a function of pressure. And especially when you look at your deuterium, it has a huge change in volume at the phase transition that is just the Mott transition. So a small change in the structure can give you a big change in the volume, and it's worse even in the actinides, but I don't want to focus on them for now. I don't know the temperature in this case. I know the temperature for the, okay, so for, so it's a bit above room temperature? Yes. For plutonium, it's a few hundred degrees.
Isn't this one of the issues with the maintenance of the nuclear stockpile, the phase transition in plutonium? The structure transition?
I think it's pretty well known experimentally, but properly classified. So I don't think you have to understand it to keep it safe. You just have to measure it and to observe it. But yes, one would like to
that's accessible because
understand that. What makes it interesting there is that the most Mott-like material is plutonium. It sits right there. So, but we don't want to talk about that because we're not interested in factoring of plutonium. We're interested in things that we can talk openly about and that are not classified by someone. So let's look at real challenges. Superconductors. I want to have a room temperature superconductor. I want to model the superconducting properties of the material. And these are tiny energy scales. These are electron volt scales or less. We want to study multi-ferroics materials with switchable electric, magnetic, elastic properties. Topological materials with unusual band structure, topologically insulated to build our quantum bits, maybe. We want to have dyes, big pigments, non-toxic dyes with the right colors we want. We really want the accurate description of transitions between localized orbitals. And we want to have non-rare Earth-based permanent magnets so that we are less dependent on China. So there's lots to be done if we can accurately describe such materials. But It's hard on a classical machine. It's hard on a quantum machine. So we want to do some hybrid kind of classical quantum method. We want to either look at the simplified model, like the Hubbard model, solve that, or we want to mix methods we use for the Hubbard model with DFT to make self-consistent DFT plus strong correlation solution. Let's talk about that. So first, how can we do these things on a quantum machine? For the Hubbard model, they've been built. They're quantum simulators. They've been tested, validated, they work. That has been one of the runners-up for the breakthrough of the year in science 2 years ago. They have been tested. So what is the idea here? We can by now control single quantum systems accurately, single atoms and ions, photons, quantum dots. And now we can just build a quantum model. We can essentially build a Hubbard model, for example, and then measure on it. And this brings me to the classification of computing devices. The first computing devices were analog. The Greeks and the first one known as the Entanglement, the mechanism found in an old Greek ship for that calculated the motion of planets. This was special purpose analog. Nowadays we have a programmable digital machine. What we're going to now is analog quantum machine, a quantum simulator. I want to build a Hubbard model. And then the next step will be the quantum computer running Windows Q. That's my code name for it. So, but let's first stay with the quantum simulator. What do we do there? The first example was Bose-Einstein condensate. We take the rubidium gas, we cool it to nanokelvin temperatures. It's in a metastable gas phase. And when you at those temperatures, these are the bosons, they all condense into the same ground state in a trap. When you then look at the momentum distribution function, you cool it, you see a sharp peak appearing at 0. These are all those atoms in the same quantum state at rest. That's the Bose condensate. All of the atoms enter the same quantum state. And that was first seen in 1995 and gave the Nobel Prize to Kettler, Cornell, and Wyman. Next, one can take this and one can add an optical lasers and the optical lattice from lasers on top of it. And then you have bosons or fermions and nickel atoms in the lattice. You can build it. It gives you a huge optical table, lots of lasers, lenses, mirrors, and so on. It takes about 3 years to really calibrate it, get it controlled. It costs a couple $1 million to build. Then you have it, and you can take pictures, for example, in a quantum gas microscope of the Garnet group. They see here really in the individual atoms in the lattice. And one more thing I want to show is how can we measure properties there, especially how have people measured the momentum distribution function. There I have a nice movie by the group of Bloch. And it's very simple. You start with your cloud of atoms in the trap. Now you just release the trap, and the atoms fall down. As they fall down, the cloud expands. And the faster atoms fly farther, and so after a while, the distance from the center is proportional to the velocity or the momentum. So when you then take a picture, you get a picture of the momentum distribution function, roughly spoken. You have to take into account that it defaults for a short time only, but then this works. And this can be done for bosons, this can be done for fermions. Before doing it for fermions, the challenge by DARPA was to validate that it works for bosons. We checked that. We got from the experimentalists the parameters, which atom they used, the trap, the particle number, the entropy, and we calculated what they should see. And the challenge was that the experiment should better reproduce what we simulate, because the experiment is supposed to be an analog quantum computer for the model. So it should better reproduce the model. And here's the comparison. In the lattice at high temperatures, there's just a broad peak in the center. When you go to low temperatures, more peaks appear at multiples of 2 pi, which are the condensate peaks, and one sees the phase transition. And the experiment is noisier than the simulation, but it works and gives quite good results. Now, bosons, without a gauge field coupled to them, we can solve. They're easy to solve. And now we go to a hard problem, a high temperature superconductor. It's hard on a classical computer. It's easy on a quantum machine. We just change the isotope. We add one more neutron, and the boson turns into a fermion. And essentially, we use the similar setup. And then one sees the Fermi surface in the momentum distribution function. But can we solve the problem of room temperature superconductivity with that? The answer is no, because cooling is a real challenge. We have to cool it to tiny, tiny, tiny energies. We would have to cool it to picokelvin and lower. And essentially, they just cannot at the moment go low enough. And even if they can do a Hubbard model, but not a real full material. So one can make progress here, but so far the classical simulation methods keep up. So, but it's hard doing that on a quantum simulator, and so I'd prefer to have a programmable quantum computer. And here the scaling is much better than the worst case I said in the morning. Because first of all, for the one-body term, we have the hopping. The hopping is local on this lattice. In this case, there is a way, if we use twice as many qubits, we can do it in constant time. It doesn't scale with n. The interaction is local. I have just n terms instead of n to the 4 terms. It's just the Hubbard U. But all terms can be parallelized. The hoppings of the odd terms in the x direction, the even bonds in the x direction, the odd bonds in the y direction, the even bonds in the y direction, and all of the Hubbard U's. Just 5 steps, and those 5 things can be done in parallel. So the scaling becomes constant instead of n to the 4 log n. Therefore, it improves. Well, for the full Coulomb, that was my 10 to the 9 times n to the 4 times a log n, maybe, and more factors. Here, I might have 5 terms. So there's a 5 here, which I turn into a factor of 10. Then the other advantage is I'm looking only at the correlated band and not at the total energy. So I look at the much smaller energy range. But I still have to be careful about what accuracy I want, and I might want a fixed energy, but the total energy grows with n. So the error I want to have should shrink with 1 over n. So I get a scaling of about 10 to the 5 times n instead of 10 to the 9 times n to the 4. And this now looks much more realistic. So here we can do big systems now. 50 times 50. And we need such big systems here because it's really strongly correlated. And so we have here this work with Brian Clark, Dave Wecker, and Gerd Chaitanayak about how we can solve the Hubbard model on a quantum computer. For the basic idea, we take an idea that we had for the quantum simulator. We move it to a quantum computer. We take single plug heads that we build. Then we couple them adiabatically and so build up the ground state of the Hubbard model. Then we measure what we want to measure here. Correlation functions, spectral gaps, response functions. conducting pairing. And on systems of up to 8 sites, it gets implemented, encoded, and run on liquid by Dave Weck until shows the liquid tomorrow. That way we can check how the scaling goes, how slow we have to couple the plaquettes, that it works, that the state is prepared, what is the cost for the measurements, so on, and that we can do, and I think the Hubbard model should be solvable. Now, the Hubbard model has been called a spherical cow. Consider a spherical cow of radius r. It's a very useful approximation for a physicist, but it's not relevant for any material. If you talk to a physicist, they think it's great. If you talk to a material scientist, then I've asked one and she said, okay, if you solve the Hubbard model, I'd be totally bored because it's not relevant to anything. Now, in the meantime, that has changed because I've challenged her to build me a Hubbard model material. But the methods we have learned so far to solving the Hubbard model, they can be applied to materials, and especially something called the dynamical mean field theory, which is quite successful for describing materials near the Mott transition where the physics is local. This is basically a mean field theory on a quantum level. So let me quickly review mean field for spins. You take a spin in a lattice. You look at just one spin, and the rest you replace by an effective mean field. And then you solve that self-consistently that the mean magnetization of the spin should be the same as the mean field coupling to it. In DMFT, you do the same for a quantum model, but now it's not static, but the electrons can hop. You start from a lattice model, you pick out a single site or a cluster of sites, a cluster of atoms, for example, and then the rest all around you replace by a self-consistent path, and you let the atoms hop from the site to the path and back. And that way you greatly simplify the model. And as long as the physics is local, like in the Mott transition, that it essentially turns from an itinerant problem to a localized one, then this is a pretty accurate method. And it can be improved by making using not just one site, but 2 or 3 or 4 or 5 sites for the impurity. What is the problem here? I take my lattice model. From the lattice model, I calculate so I take the path around. I solve the path exactly because the path is one of non-interacting electrons. That gives me a Green's function. I then get a site coupled to a path around. That I have to solve a single site coupled to a path. Once I've solved that, I measure the Green's function on the site. And then I want to find a lattice Green's function that has and then I look for the lattice model that has the same local Green's function. So it's like a mean field theory where the self-consistency is in the local Green's function. And the expensive part is still solving that quantum impurity problem. But this is now a much smaller problem than solving the full lattice model. How do we solve that? On classical machines, we made a progressive effect of 1,000 to 100,000 over the last few years by going to newer the Coulomb methods that work in the continuous time and are quite fast. So there we make no Trotter error, and that allows us to go about the factor of 1,000 faster. What we can now do is, well, before we needed the supercomputer to solve a single orbital DMFT that now takes just minutes on a laptop. And on the supercomputer, we can do 5 to 7 orbitals with the full Coulomb the interaction, and that way we could look at the F materials like cerium. People in some the national lab look at the actinides, but so we can go up to about 5 to 7 orbitals. Yeah.
Do you mean here also non-local exchange terms which
yes.
induce a sign problem?
Yes. Okay. There's no sign problem because we go into the eigenbasis of the localized cluster.
Those, work at the, okay.
Yes. So we work in the eigenbasis of the of these F orbitals.
Expanding in the coupling, not in U but in T.
We're expanding in the hop into the path, and that's the key here. Then we can do it.
Okay.
But it means because we have to go to the eigenbasis of those correlated orbitals, that the scaling is exponential in that size. So that's why we are stopped at 5, typically, and at 7 if we make some truncations. And that's our base in which we do the Monte Carlo then. And so this one can do for simplified models. One can also do it for materials. What we do there is we start from the DFT the calculation. We pick out a certain set of local the one-year functions from the bands, which model the F or the D orbitals. And then we pick out those that we want to model in a fully correlated way. We add in the full microscopic Coulomb interaction, a screened one, which makes it a bit harder for those. But then the problem is we have already counted the Coulomb interaction because we already have it in the DFT. So we have to subtract the double counting correction because we have already treated the Coulomb term in DFT. And that's that's a problem because that's ad hoc here. Because it's not a pure F state, it's an F mixed hybridized with an S or a P. And so it gets hard to separate it really well. But one can try it. And then one sees here, for example, for some the perovskites, we go from the strontium vanadate over calcium vanadate to lanthanum yttrium titanate. And as one goes here, one increases the ratio of the Coulomb repulsion, the local U over the bandwidth. And at some point, a gap opens up at the thermal surface and it becomes the Mott insulator. LDA doesn't see that. That's the thin line that stays in metal. In LDA plus DMFT, you see the Mott gap opening. By experiment, I have a slide that shows some things from experiment. There's a spare one which I can show, and it's I have to unhide this.
Well, I didn't mean to interrupt.
No, they're fine. So here's some data from experiment for the yttrium titanate that has, so that's the photo emission spectra. And you see there's a gap here, and there's a peak at around minus 1.3 electron volts. If you go here, there's a peak around minus 1.1. So it's roughly in the right place. For the strontium vanadate, that's still a metal. So it looks qualitatively okay, quantitatively semi-okay.
How did you obtain the J and U parameters for that? I mean,
that's the big problem here. So you have to, so that's one of the problems. You have to find out what is the screened local Coulomb interaction that you should use for the model.
what I mean is, I'm not saying that this is what happens in this calculation, but certainly in some DMFT calculations, the parameters are not independent of the experiment. Right?
Oh yes. What you do is you have the double counting, and you just fudge your things until it fits.
Yeah, right.
And if it doesn't work out, you don't publish it. That's why I'm not doing this. I'm inventing methods for them to use.
Okay.
I've written 1 or 2 papers there just to show that it works, but then I've withdrawn again. I said, no. Yes. Yes. The big problem is, what is U? How do you get the Hubbard U? Because it's not the bare Coulomb interaction, it's a screened one. It's screened by the other bands. Yeah. And the J term also, it's screened. So that's the big problem. How do you get reliable values of U and J? And let me show you another slide then, which was just the next one that I wanted to show. That was a calculation done with a simplified model. So this was done 10 years ago before when I could do the full Coulomb interaction with the new methods here invented. At that time, people, that was the Kotler group, they looked at the plutonium with just the Hubbard type model, just the U term. And the problem in plutonium is that in DFT, the volume comes out in a GG8 comes out 30% too small. It's just totally off in the volume of the unit of the unit cell. As you add a U, and now you change the U, as you change the U, the minimum changes and starts shifting, and then it jumps up, and this is normalized here to the one of the experiment. And once you have a U of about 4, then it starts agreeing. And when you change the crystal structure from the FCC to the BCC, that it should be then the energy is the lowest. So that way you can start getting at least qualitatively right answers for the correlated materials, but there are still challenges. Because we're limited to about 5 to 7 orbitals. We have the double counting correction. And it's hard to get the U and the J parameters, the screened Coulomb and the Hundsruhle exchange. So, and the double counting also sensitively depends on how we choose our correlated orbitals. Because the band that I showed is not just purely F, it's F hybridized with S and P. So what can a quantum computer help? What if we can go to about 50 instead of just 7 orbitals? We can avoid most of the double counting problem by including the S and P bands as well. And then it's much less severe. We can include a few more bands, and the screening problem becomes less severe. And the U is then more microscopic. We can go to the bigger the unit cells, like multi-layer cuprate superconductor, or the alpha phase of your plutonium, which is the interesting one at the room temperature, where there are 4 atoms in the unit cells. So I need at least 28 orbitals to have just the F orbitals modeled. And I can make it more accurate by including more unit cells. For the Hubbard model, we've shown that if you want to go to about room temperature, you need to go to about 100 unit cells to really get it accurate. So here, okay, in the hardest regions. So here again, by going to more unit cells, one can make it more accurate. So I see a big potential here for going way beyond what we can do now, just by going maybe from 7 already to 15 orbitals, for which we might need 30 qubits, 40 qubits. We could do much more. Okay, so we need 30 qubits for the correlated ones, and maybe 100 simple ones for the bath, which is non-interacting, where things just hop to and back. So we might need about 100 orbitals in total, or 100 qubits or 200 qubits, but the correlated hard part might be only about 15 orbitals, and we have something that goes way beyond what we can do now. And so here, things can work easily. I'm not saying that that will solve all the problem, but we go way beyond what we can do now. And so what we then want to do is we want kind of a hybrid simulation, LDA plus DMFT plus quantum computers to solve that. And that can have the big impact here. The second way is models like the Hubbard models. And so what I'd say is what we should look for is kind of some hybrid classical plus quantum methods where we reduce the complexity of the quantum problem that we solve by treating some things approximately and then finding a good way to correct for it, like in the DMFT. And we need something like that also for molecules, and you have the other problem, and that's what we should maybe think about. So if you think I've been pessimistic, it's just because first one has to acknowledge that one can't just do it brute force, and now we have to be smart and find out ways how to solve it. Thank you for staying, for listening.
Matthias, you finished very promptly. Do you have time for questions?
Yeah. We have 6 minutes for questions, then we should go to the shuttle.
Yeah. What is the complexity class of the Hubbard model? Could you just remind us?
Oh, the Hubbard model? I think I can build Hubbard models that are where finding the ground state is at least NP hard. But the simple square lattice Hubbard model for the cuprates, my belief it's in PQP because nature finds the ground state easily and the thing goes superconducting. I can't prove it, but that's my feeling.
It's hard to ask that question, right? Because you have to ask about a question about scale, right? And the Hubbard model doesn't have enough parameters in it unless you play with spin glass.
I can put the Hubbard model onto special lattice and turn it into a spin glass. I can build a spin glass from the Hubbard model.
So then you have enough parameters to ask that question reasonably, but then it's not the Hubbard model you want to solve because it's a spin glass. If it's the Hubbard model you want to solve, there aren't enough parameters to encode essentially enough problems to really talk about whether it's a...
But the Hubbard model on a square lattice, I believe, because the materials find the ground state quickly, I believe it's in PQP. It might be in P, but I don't know that yet.
I don't know if I cut you off. So. Okay, so actually I had a comment on the last spin glass thing, but then I had a question, so maybe I'll just hold the comment. So there have been a number of comments about, say, spin glasses, and then there being problems because one wants to find the ground state, and trying to find a true ground state in that case is very hard. But it might be misleading. I mean, it might be that the Hubbard model is some kind of spin glass, but nature doesn't find the ground state. And that's actually a situation you see in biology and proteins. So for a long time, the protein folding field was concerned with finding the ground state of a protein which explores an exponential configurational space, and they were worried about how to find the ground state. But the fact is, in many cases, nature doesn't find the ground state; it just finds a metastable state. And so the relevant physical state is not the thermodynamic stable state. So perhaps, one could say. I mean, what I'm saying is maybe we shouldn't worry so much if in nature there's a spin glass Hamiltonian. We don't have to find the ground state.
If nature have, if there's a spin glass material and you want to model it, then yes, then you might just want to see, hey, it looks like a spin glass, and that's good enough. And nature can cool it much better, but that's it. But then typically spin glasses we want to solve because we map an optimization problem to a spin glass like on the D-wave machine. And then we want to at least get a good low energy state.
Yes, I think all wants a good low energy state.
Yes.
We need the So I was going to say, with respect to hybrid approaches, I mean, where you treat some degrees of freedom differently, then of course I think in chemistry this is what we always do.
Yes.
So it's really a question of machinery that hasn't been transferred into solids. It's just so much work. But I mean, as you're talking about the active space concept and so on and so forth.
Maybe I just make a comment on what Garrett just, the distinction Garrett and Matthias were talking about, finding the exact ground state versus a good low energy state. one of the most important open problems in quantum computer science is QPCP. So it's known in the classical world for about 15 years that there are NP-complete problems for which it is just as difficult to approximate the solution as to find the exact solution. And the quantum mechanical analog of this is whether this is true for QMA complete problems in general, whether there are Hamiltonians for which it's just as difficult to find an approximate ground state, a low energy state, as it is to solve them exactly. So I don't think there's a betting pool on this conjecture, but it's really like one of the key open problems.
So, just like do you see like a physical machine analogy to D-wave, starting with the Hubbard model and do d-body quantum computing?
You see, we already have a Hubbard model machine, or many of them, with near quantum gases and so on, and they work pretty well, and they get what we get. And for all of the static and thermodynamic properties, they've been a nice challenge for us, so that by now we have quantum Monte Carlo methods like the continuous time QMC solvers for the DMFT that essentially give the same results. So for thermodynamic properties, these experiments challenged us to beat them, and so far we've won. For dynamic properties, like I mentioned, it's very different. So there, of course, they win, because for quantum dynamics, we have no way of doing it. There's a huge sign problem that we just can't solve except for very short times. But these things, so in those things, we take the atoms and use the atoms to model the fermions, and they interact by the van der Waals interactions, Lennard-Jones-like, which is short range. So it's a contact interaction. It gives me a Hubbard U. But it cannot really go easily beyond the Hubbard U. I could build a dipolar molecule in a lattice. That's what people work on now. That way one can get a dipolar coupling. That's hard, but and one can use ions and get the unscreened Coulomb. But I can't really build the band structure for a cuprate this way. So to go to a real material, there are two ways. I either use the quantum computer, or I learn from the Hubbard model about the new classical method, which I could then apply to the material. We're trying to go both routes now and see who will win, the quantum computer or our classical ideas.
I think because of the time, we should thank Matthias. Maybe I should ask.